Hey guys, we're doing section 2 and 3 here in chapter 15. So we're going to talk about the characteristics of stars and figure out how they're classified. What do astronomers use to measure the distance of stars, and what an HR diagram is, and how do astronomers use it. So stars are classified by a couple different ways. They are huge spheres of glowing gas, mostly hydrogen, and the characteristics used to classify them are the temperature right here, the size, composition, meaning what are they made of, and brightness. The star's colors can be deceiving. The coolest stars actually appear reddish, while the super hot ones, the hottest stars that we have, are actually blue. Our sun is in the middle. It's a yellowish color. And they vary greatly in size. You can see here the difference between a white dwarf on the left versus the large star on the right, which seems pretty big. But then if you look at this is the giant star, and you can only see the very, very edge of it. So giant stars are typically 10 to 100 times larger than the sun, which is our star right here in the middle, and more than 1,000 times the size of a white dwarf. We use star spectrums here. We use line spectrums to identify the chemical elements of a star. So each element produces a certain thumbprint, you can almost think of it as. The spectroscope can be used to look at these and figure out if you see this thumbprint with the black line here and here, here, and here, then that would be hydrogen. But if the black lines are right here in that yellow range, and there's only two of them super close, that's sodium. So each star burning gas, if it's made of whatever type of gas here, then we can identify it and say that, oh, it's sodium, because the spectrograph looks like this. Now, parallax is the apparent change in position of an object when you look from different places. So you can think of it this way. If you're sitting right here in a movie theater and you have the screen, this movie's going on the screen, and this lady's sitting in front of you, she's blocking kind of the dinosaur from you, the dinosaur's face from you. But if your friend is right next to you and sitting more directly behind her, the lady, here's the screen, the same image, and the lady's more blocking this little bird and the nose of the dinosaur. And the lady hasn't moved and the screen hasn't moved. It's just that it's the parallax that's talking about your point of view. So when we look at this, astronomers use parallax to measure the distance. So when we're orbiting around the Earth, when we're in January, we might measure the star here, and then we measure it again, the exact same star, over here in July, and we take the average. So this is what the stars look like in January, B, C, D, and A. Over here, this is what they look like in July. Again, the stars haven't moved. It's just that our view, our point of view has moved. And you need to know light years. Light years is the distance that light travels in a year, which is about 9.5 trillion kilometers. We use light years whenever we're measuring outside of our solar system. So there's two different kinds of brightness. It depends on both its size and its temperature, and it can be described a couple of ways. Brightness, apparent brightness, is how bright it seems to us here on Earth. Like our sun seems very, very bright, but that's only because it's so close to us. Absolute brightness is the brightness a star would have if it were at a standard distance. So if we take all the stars and we line them all up with our sun, there's going to be some of those stars that are brighter than our sun, and some that are not as bright as our sun. That's absolute brightness, when distance isn't a factor. Then you have an HR diagram here, and they use this to classify stars and to understand how stars change over time. And our sun is actually right here. It's a main sequence star, like 90% of the other stars. So all of this blue area here, these are all main sequence stars. That's what most of the stars are out there. We have some over here. These are like white dwarfs. We have a few over here, supergiants, and we have giants over here in this area. So we know as we increase up here, the brightness, the absolute brightness, not apparent brightness, not what it seems to us, but the absolute brightness increases. And the temperature gets hotter. Remember, blue over here is super hot on this side, and it gets cooler over here. Red is actually cooler. So, and then if you have a blue or blue-white star, that's very, very hot. You have white stars here, yellow stars here. This is where our sun is. And then red, orange stars in red. So those colors go actually along with the surface temperatures down here at the bottom. Okay, section 3, how does a star form? How long will it exist, and what happens when it runs out of fuel? So all stars begin their lives as part of nebulas, large clouds of gas and dust spread over an immense volume. Gravity pulls them all together, and you get what you call a protostar. But in order to become an official star, the protostar must become so hot and dense that nuclear fusion starts. So a star is born when nuclear fusion starts, not when it becomes a protostar, when nuclear fusion starts. So you've got this nebula here, and you can go to a low mass star, and then that can turn into a lower medium mass star. It has this cluster stuff. It condenses here. It can get to a red giant. It continues over here. It moves into a planetary nebula, and then it can turn into a white dwarf. After it runs out of fuel, it becomes a white dwarf, which is a neutron star or a black hole. When we look over here, then we're talking about high mass proton or protostar. So we have this nebula, then it goes to high mass. High mass star, it starts to kind of gather because of gravity, can turn into a supergiant, and that would then turn into a supernova, which is a neutron star or a black hole. This one here, with the smaller stars, it ends up as a white dwarf when it's a low mass or medium star. This one, high mass protostars end up as neutrons or black holes. We're not going to go into the depth of star. I'll show that to you in class. But we also have these neutron stars and pulsars. There are spinning neutron stars that emit steady beams of radiation. And astronomers can briefly detect those flashes of radiation as it's spinning, rotating on its axis. The neutron stars are the remains of high mass stars, and they may contain 3 times the mass of the sun, but be only 25 miles in diameter. So super, super compact and super, super dense. Black holes are the remains of most of the massive stars. They collapse into a black hole. And here it shows a black hole pulling matter from a companion star. So sometimes we can have 2 stars right near each other, and it's pulling matter for that star. Their gravity is so powerful that nothing can escape those black holes, not even light. And again, we'll show this little video of neutron stars and black holes in class. And that's it.